I'd like to thank everyone for joining us in today's webinar, Advances in HydroGeoSphere over the last decade. Over the past decade, HydroGeoSphere has continued to evolve into one of the most advanced and widely trusted platforms for fully integrated hydrologic simulation. What originally began as a bit ambitious effort to bridge the gap between groundwater and surface water modeling has grown into a comprehensive modeling framework supporting increasingly complex environmental and water resource challenges across academia, industry, and government. The evolution has included major advancements in parallel computing and high-performance simulation capabilities, improvements in numerical methods, and physical process representation, and the introduction of entirely new new workflows and applications, from particle tracing and source zone identification to tunneling simulations, dynamic meshing, and advanced water management practices. HydroGeoSphere has continually expanded both its capabilities and its impact across the hydrologic modeling community. In today's webinar, we'll take a retrospective look at many of these developments and explore how HydroGeoSphere has transformed over the last decade to support larger, faster, and more sophisticated integrated hydrologic simulations. To guide us through this discussion, we're joined by Dr. Hyoun-Tae Hwang, Director of HydroGeoSphere here at Aquanty. Hyoun-Tae is a senior environmental scientist at Aquanty and an adjunct assistant research professor in the Department of Earth and Environmental Sciences at the University of Waterloo. His work has focused extensively on parallel computing, integrated climate and hydrologic simulations, and large-scale hydrologic modeling. During his PhD research at the University of Waterloo, he contributed to the development of several advanced numerical simulation algorithms, including the parallel computational framework for HydroGeoSphere itself. Today, Hyoun-Tae continues to play a leading role in advancing HydroGeoSphere's development and computational capabilities, making him uniquely positioned to walk us through the major milestones and innovations that have shaped the platform over the past decade. Hyoun-Tae, thank you again for making yourself available for today's webinar. With that, I will pass it over to you.
Yeah, thanks, Yoko. It was a great introduction. Today's my talk is as Yoko mentioned, the advances in HydroGeoSphere over the last decade. Thank you all for coming to hear my presentation. Today, I'm Hyoun-Tae Hwang, Director of HydroGeoSphere, and also adjunct professor at the University of Waterloo. So my main talk is advances in HydroGeoSphere over the last decade. So before just getting into the today's talk, I would like to mention that the HydroGeoSphere has been developed for about the last 3 decades. So early stages, the main developers, including Professor Ed Sudiki, Professor Renee Terrian, Dr. Youngjin Park, Mr. Rob McLaren, and Dr. Saurabh Pandey actually made a biggest contribution for establishing HGS. So definitely there are many other developers over the world, but they are kind of main developers. So without their effort, the HGS would not be possible currently. So after stabilizing the HGS, we actually I involved with HydroGeoSphere group, Dr. Ed Sudiki's group, and I developed the various features. So my main talk is just focusing on my kind of current project and also development for last decade. And then currently, our development team not just for HydroGeoSphere, but for actually wet atmospheric development team and also HydroGeoSphere development team, including Dr. Killian Miller and then Mr. Ali Charpines. They are very kind of making a significant contribution for improving HydroGeoSphere feature and improving accuracy of the HydroGeoSphere. So let's get into today's talk. And so I just organized my kind of development for last decade into 4 milestones. Just starting from the beginning of the rapid growth with high performance computing system. So one thing I would like to mention before getting into the detail of this milestone, actually this development would not be possible without the collaboration across various partners, including academia, industry, and also government. So with that, the strong collaboration with those partners, we actually evolve into the next phase of HydroGeoSphere, improving accuracy and improving, developing various features. So first the milestone is the beginning of rapid growth with high performance computing. This is my PhD work. So at the time, it's been about more than 15 years since I developed this parallel computing algorithm. That time, we start to just implement the HydroGeoSphere to the various real-world applications with large-scale models such as Canadian continental scale model. That actually uh, is actually that the complexity of the model is actually greater and greater, and then that require actually higher computational demand. So we need to develop some kind of computing efficient model. So by implementing high performance computing. So and then we now just we develop we actually that the parallel computing algorithm is kind of normal, but at that time it was not that common. So now just we are kind of easily just utilizing our computing machine with the multi-cores. So the detail of this parallel computing is about very kind of simple. Just I developed a privatization scheme with array chopping that is actually split into the number of cores. So each core working on this matrix, and then core 2 working on this matrix, and then 3 and 4, and then the number of cores actually can split into these chunk of matrix instead of using this whole matrix. So that is what I call is a privatization scheme with array chopping. So this case, each core doesn't need to compete in with other cores to access the memory. Just a privatized memory for each core. Then we don't need to just each core doesn't need to compete for accessing memory. So that actually speed up by up to 12 times. That is something comparable between Sprinter versus a Formula One car. It is not that comparable. Actually, the speed up is quite significant. And then we can utilize our high performance computing center. And also users can also use their own multi-core desktop and laptop, so without accessing to the high performance computing center. So for example, regarding the speed up, for example, that time we try to run a Canadian continental scale model that is consisting of about 3 million nodes and then almost 6 million elements. It took about 3 months to obtain the simulation result. Using our parallel computing algorithm, we were able to achieve the simulation result within a week, which is a significant improvement in computing efficiency. So next phase is just so we try to implement more physics and to understand the detail of the phenomena in the nature. So we advance this in physics and implement additional numerical methods. So that the main examples are source zone identification and freezing thaw processes and climate change impact analysis. First, we can look into the source zone identification. So we expand the backward probability model to improve the computing efficiency and also the accuracy of the source identification. Just to expand, it was mainly focusing on the groundwater system with 2D, but we expand that to the 3D model with also variably saturated zone. So first, the backward probability model is literally opposite to the forward model. That is starting from source zone. We don't know, but they're just starting from source zone and then run a solid transport and then detect the concentration at the monitoring well. However, backward probability model is just starting from the monitoring well, just where the contamination is detected, and then run the simulation, and then trace back to the source of the origin or source of the contamination. So that easy to kind of identify the source zone because we just simply start from kind of monitoring well. But for the model actually takes a lot of time because we don't know the exact solution. Then it requires lots of iterations to identify solution. And however, the backward probability model is just simply starting from the monitoring well. And then new methods actually combine the multiple probability density functions and also improve the multiple contamination sources. So this is one example of a backward probability model. So you can see that is actually representing source of contamination and then moving backward upstream, which is opposite to the groundwater flow direction. And the final result will be the map probability map of the contamination. So you can see the dark blue representing the high that the red represent the color red represent the high probability of the source zone. So we can just overlap the multiple backward probability model simulation. Then we can identify the highly possible contamination sources. And next is physical processes. That is actually kind of unique physics we implement for identifying the active layers in Antarctica. That is actually for the active layer is just frozen during the winter, and that play as a groundwater aquifer during the summer season in Antarctica. So that is a very, very important layer that are connected with the surface water and groundwater system in our cold region. So in order to estimate active layer in Antarctica, we collect the sample in Antarctica, Baton Peninsula and Antarctica, and then perform the lab experiment in the cold system. So we calibrate this column test and then apply the calibrate the model to the Baton Peninsula, Antarctica. So you can see the surface water depth distribution example, and also the interactions between surface water and groundwater system. That is an exchange flux. So where the red represent the strong exfiltration flux. That is a groundwater flow from groundwater system to surface water system. And also the blue represent the infiltration. That is a water movement from the surface water system to groundwater system. So you can see the blue is mostly around the land side, and the red represent the groundwater recharge seep into the recharge that infiltrate into the groundwater system. So this is a very, very important information for identifying the strength of interactions between surface water and groundwater system. And next is a climate change impact analysis. This time we also coupled work, weather research and forecast model, that is the atmospheric model, and combined with HGS, HydroGeoSphere model. Then we simulate the atmosphere, surface water, and groundwater framework, and then that applied to the Athabasca River basin that covers about 160,000 square kilometers. And then we you can see how we build the subsurface model from the bottom of the model to the surface system. And we implement the various data sets such as climatology, land surface, land cover, soils, and geology. And you can see the climate change impact for the mid-century and also end of century. So these are examples for mid-century simulations. So then we can predict how the surface water and groundwater system interact, and also the water availability in mid-century. And the next milestone is improving the workflow and applicability. So these are actually these developments were made through the collaboration with engineering projects. So these are the examples are tunneling, water management, and mining, and nuclear safety. So first, the tunneling. This is a very important feature for estimating groundwater seepage through tunnel. So that underwater construction, such as nuclear repository simulation, nuclear repository construction, also the subway construction, that is very, very important to estimate the groundwater seepage through tunnel. That is related to safety of the tunnel, and also they need to set up that discharge system before just starting the tunnel, starting the construction of the tunnel. So we previously the tunnel boundary condition was a very simple, just a seepage boundary condition, but this actually causes numerical errors and also unstable condition for overall the simulation. So we implement a new third type boundary condition and taking into account the tunnel structures such as damaged zone and also tunnel wall pressure. Those things are implemented to the tunnel boundary condition, and then we apply this to the kind of metropolitan subway system in the metropolitan city Seoul. So these are very complicated subway system, and also we implement the third type boundary condition, tunnel boundary condition, and estimate the effect of this the subway system to the overall metropolitan city. And then next example is the wastewater nuclear waste repositories construction. So you can see these lines are representing tunnel boundary condition. Actually, these are tunnels to the nuclear repository system. So this is a nuclear repository, and then these are tunnels pathway to this repository. So this one is actually successful to estimate the groundwater seepage through tunnel, so that they can prepare the drainage system, groundwater discharge system during their construction. And next example is water management. So this time we develop, so anthropogenic activities actually creates a new system, such as sprinkling, water distribution, and dam operation. These are actually not nature. So we need to implement the new boundary conditions. So such So to represent this water distribution system, then we developed the boundary condition linking that links one boundary condition to another boundary condition. For example, here we extract the surface water and then discharge the surface water into the groundwater system. So by linking two boundary conditions, we can represent that this water distribution system. And next is dam operation here. So here, just block the water and then make a reservoir behind this dam. So we implement a numerical dam that by disconnecting the link between two nodes, then we can build a numerical dam. Then behind this numerical dam, we can simulate the water reservoir behind this numerical dam. So by using these two numerical approaches, boundary condition linking and numerical dam, we can simulate the complicate the water resources management system. Here we apply these two numerical approaches to complicate water management system here. So one dam, two wells, three wells for the water supply, and then 5 farms and one municipality. Those are actual water demand components. So there are very complicated interactions between water supply and water demand system. So depending on condition of water demand and the water supply, so we have a complicated water supply and demand estimation with respect to each component. The municipality, farm 1, farm 4, farm 5, those things are actually very, very complicated interactions between water supply and water demand components. So we successfully estimate these complicated conditions. And next example is mining. So there are two, regarding the mining operation, there are two main phases, excavation and the reclamation phases. So previously, regarding the groundwater, that environmental effect of mining processes is just a separate simulation for the excavation only and then reclamation only. So there is no connection between excavation to reclamation simulation. So that case, it is a very, very kind of not that as robust as at the same time, and it is not that exact simulation because these are actually disconnected and that involves the unnecessary assumption like boundary conditions and also initial conditions. So in order to improve these kind of problems, then we actually implement the dynamic meshing scheme just by moving the elevation of nodes upward and downward. And then for lowering the elevation of the nodes, then we can represent excavation stage. And increase the elevation of the nodes, then we can represent the reclamation stage. Here you can see the example of this excavation and reclamation stages. And also we apply this dynamic meshing scheme to the multi open pit mining sites in Ontario. So dark blue represent the surface water depths is actually deeper, and then dark brown represent the surface water depth is shallow or almost a zero water depth. So you can see the kind of water depth is actually increasing deeper than during the excavation stage, and then the water depth is getting shallower than during the reclamation stage. And you can see the cross section of this area. Then you can see the dynamic interactions between surface water and groundwater system during the excavation and reclamation stages. So this way we can simulate these two main processes continuously, and at the same time we can also estimate the dynamics between surface water and groundwater system. And next is nuclear safety. So we established the main processes to estimate the uncertainty of risk of the radionuclide species in water the nuclear power plant or nuclear waste repository. So first step is just calibrating size scale model using field data, pumping test and press test. And then we set up the size scale model with then a heterogeneous field, and also perform the uncertainty of the model because it is a non-uniqueness, and also the calibration that the number of observation is not much enough for identifying the exact model. So we need to perform the uncertainty of the model. Then based on the uncertainty of model, then we perform the risk of the radionuclide. If there is a leak of the radionuclide into the groundwater system, then we can simulate, we can provide the range of this radionuclide concentration with different locations. And then also same time, we can also provide the main behavior of the radionuclide through the variable saturation zone and the groundwater system. So this way, this information is very important for groundwater or the radionuclide management team for setting up the new policy of the radionuclide if there is a radionuclide leak. And then the last milestone is the advances the computational performance. We actually improved the computational performance from the beginning, but still there is still demand for improving computing efficiency and as well as accuracy of the simulation, because these days actually the model is actually complexity of the model is actually greater and greater, and the usual demand is beyond the technical state capacity. So we improve the computing efficiency and accuracy further for the for more complicated conditions. First example is density dependent flow and solute transport. This one is actually kind of nasty problem because it creates a huge nonlinearity for the flow, and because it involves the density dependent flow and solute transport. So this time we implement the pseudo transient parameter continuations method. The name is quite complicated, but it is simple. Just simply changing the parameters from especially for the density of seawater, from fresh water to the real density of the seawater. So here, initially we assigned the density of seawater as a fresh water. It is the same. We treat as a fresh water, but the concentration is for just representing the salinity of the seawater. So you can see initial stage, then you can see the clear boundary between seawater and then freshwater. And then you can, but this part is a seawater, but the density of the seawater is actually freshwater. So that's why we see the clear density of the, clear density of clear boundary between seawater and freshwater. And then later, we increase the density of seawater slightly, about like 10%. Then you can see the boundary between seawater and freshwater is slightly inward, so then land side because of density effect. And then increase the 10% of the density of seawater, and then you can see the boundary line is actually moving inward because of density. And then later, if we assign the full density of seawater, then you can see the final stage of the density seawater intrusion for the density dependent flow. So the the name, the pseudo-transient parameter continuation. That means slightly changing the density of seawater from fresh water to density of seawater. So that regarding the computing efficiency, and then you can see that some location after some simulation time, that the density change of head and change of concentration drastically decrease with simulation time. That means that it is a stable. The simulation is stabilized compared to the general approach is slightly decreasing with simulation time. That means it requires a lot of numerical iteration, linear and nonlinear iteration, as well as requires a lot of simulation time. So while and our approach actually drastically decreases with the simulation time, that means the accuracy is higher, and also computing efficiency is also faster, higher, greater than the general approach. And next improvement is a CPG phase boundary condition. When it comes to CPG simulation, that is actually very straightforward. But when we apply to the real world application, that actually creates a huge complexity, and also this creates a nonlinearity. As you can see here, that general CPG boundary condition approach is a very simple, just like a switch boundary condition, so-called switch boundary condition. If the water level, that black line, is below the surface elevation, that is up, no boundary condition, no flow boundary condition on the surface. However, the groundwater level is above the surface elevation, is actually on. That means a flux boundary condition. It is okay, actually, that before the below the groundwater surface, there is actually nothing happened. However, the problem is actually the transition zone, and also surface transition zone here. So we can go into the below figure, then you can see the exchange flux, and then water depth with the x-axis. So yeah, just if the water level is below the surface, then nothing happens, just a flat. And but after transition zone, that is water depth is slightly increasing, and also the exchange flux is increasing, and then later drastically increasing with this location. So this transition zone is creates a huge nonlinearity, and it requires some nonlinear iterations. So that takes a lot of time. Sometimes they actually fail to converge to the solution. So we developed actually the third type boundary condition that are flexible and also continuous with this flux condition. So we compare the computing efficiency and the accuracy of the simulation result with the general approach. So blue represent our approach, and the red represent the general approach. There is a simple switch boundary condition. So blue, sometimes at the blue, our approach actually drastically decreases with simulation time. That is a nonlinear solver iteration. And then red still requires lots of iterations. So that means it requires kind of huge iteration, and it is not stable at that still at this time. So, however, our approach is drastically decreased with simulation time that converges quickly, and then that the system is stabilized quickly. And regarding the accuracy of the simulation result, that the y-axis represent this CPG flux. That is actually compared with the integrated subsurface model that representing green line. That is almost the same as our approach. However, general approach creates a huge amount of CPG flux, even with a huge amount of simulation time. So that means it is not that kind of correct for using this switching general approach. However, our approach is a quicker and also stabilizing, quicker and provide accurate, almost the accurate simulation result compared to the integrated subsurface model. And next development is HGS machine learning model. That is currently we try to implement a machine learning framework combined with HGS, and then also improve the accuracy of the model. At the same time, improve the computing efficiency, using the machine learning. So we try to implement this HGS machine learning framework to this California state model. So on the left side, that the ocean side, that we run a density dependent model to identify the seawater intrusion areas on the coastal areas. So San Francisco Bay and LA and Santa Barbara. So we actually set up some kind of seawater intrusion warning system on the coastal side and the land side. And we also try to implement the groundwater warning system. That there are significant problems in San Joaquin Valley. So that is a very groundwater resources are very important in this area. So by implementing this HGS machine learning framework, and then we can improve the computing efficiency and accuracy of the model. So this is actually the ultimate objective is just implementing this framework to set up the digital twin system. Yeah, so in summary, just HydroGeoSphere has been evolved from the high performance computing implementation, advances in physics and numerical method, and improving the workflow, and also advancing the computing performance. So yes, we still just put lots of effort to improving their computing efficiency and also accuracy of the model. So that concludes my presentation, and now I'm happy to take any questions, any comments. Thank you. Yeah, any questions? Yeah. Thank you.
Thanks, Hyoun-Tae. Yeah, we're just opening up the floor for any questions. So yeah, if you guys have any questions, feel free to drop them into the chat, or raise your hand, and yeah, we'll just give it a few moments. Oh, we seem to have gotten one.
Yeah, I may need to check chat. Okay. Steve, ask about this future avenue of computational improvements. Yeah, considering HydroGeoSphere. Yes, definitely. We are mainly focusing on feature improvement. That is, improving the capability of HydroGeoSphere for various fields, and also at the same time also improving the accuracy of the model. So those are two things are our main objective. So then and as I mentioned before, just here we expand our capability to various fields, engineering fields, tunneling construction, and water management, and mining industry. So that is our main kind of focus on our next future development. At the same time, also combined with machine learning feature that it also improve the computing efficiency and also that accuracy of the model. So finally, we aim to build digital twin model at the same time. And currently, our real-time simulation development team, development team also improve the kind of accuracy of the real-time model, and through HCS, just HydroSphere climate site. Yeah, thank you for your question. Yes. Also, yeah.
Oh, I see we have another question.
Yes.
I can, yeah, I can unmute. Yeah, here we go.
Yeah, sure.
There we go.
Yep. Thank you.
There we go.
Thank you so much. No, first of all, thank you for that comprehensive presentation. I really appreciate you putting that together. There are two problems that I'm currently working on, and I wanted to know, I was interested on the development on the tunneling and all these new boundary conditions. So I wanted to ask, a couple of questions that are on that direction. So one of them is very small scale, the other one is larger scale. So the smallest scale is that I work on the problem of agricultural tiling, which is this kind of subsurface little tunnels, if we can think about it that way, that people install to improve drainage of fields. I think in previous versions of HydroGeoSphere, I wasn't aware that you can create these kind of hollow internal boundary conditions for that. I wanted to know if you have experience on that, because there is a significant change of a scale when you think about a tunnel and when you think about a tile. So that's question number one. The other one is related to a mining project that is trying to extract sand from a sand aquifer. And in this, the problem is also kind of related to this tunnel problem, because we expect that when you remove sand from the aquifer, you're kind of changing the density of the soil matrix. There is a possibility of movement of the sand inside of the aquifer. And I wanted to know if these two new tools that you have implemented, how would they connect to those two particular problems? And I thank you for your time.
Yeah, thank you, Ricardo. Yeah, so that is actually a good question. So the first, the water management, for the question related to water management. So yeah, definitely, yeah, the site scale and larger scale problems are quite different. And also when we apply to the larger scale, that actually requires a complexity, lots of complexities involved with this larger scale model. At that time, just we may need to kind of simplify the complexity of the model, and then we can implement the water resources management, complicated water resources management system to the larger scale model. So then the site scale model is a bit simple, but if you look into if you want to the detail of this heterogeneity and also water resource management system, then probably requires a huge amount of complexity of the model. So I would say this complexity is actually highly depending on your objective. So what you want to see, what you want to know, is actually kind of designing the complexity of the model. So yes, but definitely our kind of new features, boundary condition linking, numerical dam, also tiling boundary condition is actually applicable to whatever the scale is, just a larger scale, and also the size scale model as well. So it is if you need some kind of comment or just the help, then we are definitely happy to help your project. That's why we are here. So main purpose is just helping you guys, and then you have a successful project through our collaboration and also support. And then next is
thank you. Yep, go ahead.
Yeah. And then next is a tunneling boundary control. Yeah, also, as I mentioned before, so if you kind of concerned about the kind of the sand aquifer in your during your tunnel, then probably you may need to kind of refine that area to kind of get a detailed simulation result. That means a high quality information. So yeah, so then you can see the what happened to your kind of what happened to your kind of tunneling condition, and also you can based on the simulation result, you can design, actually optimize your design for the tunneling. You can just design tunneling through the sand aquifer, or just deviate the sand aquifer if the sand aquifer is kind of unstable, or just very important for supporting the water resources to the kind of public. So yeah, definitely, we are here for you, so your project. So our main objective is just we can we should help for your successful project.
Yeah, no, fantastic. Thank you. I think that kind of gives me a sense of for that question. Thank you.
Yeah, thank you.
Perfect. Yeah, I see we have 2 more questions in the chat as well. And if there's any other questions too, feel free to drop them into the chat.
So, okay. Maybe Larry V. Is that the next question?
Yep.
Okay, yeah. So, sorry, well, my pronunciation is not good. So, sorry about that. Just Larry V asked about just what if scenarios for water quality, and yeah. So that is actually very important question regarding the uncertainty of the model. So here, I actually kind of provide one example for risk assessment of the radionuclide kind of leak from the nuclear power plant or hazardous facility. So these steps are very important. Calibration using the field or lab experiments, and then set up the site scale model, and then run the risk assessment. But this risk assessment is based on the kind of involved with what if scenarios, such as storms, droughts, anything, just anything. Yeah, definitely anything happen, and especially it is very important to estimate the kind of risks for any conditions, because it is a very important facility for just public health. So that case, we don't know the exact parameter set. So that's why we perform the uncertainty analysis based on the calibrated model. So after calibration is done, then we need it is necessary to perform the uncertainty of the model. So based on the calibrated parameter, that actually kind of parameter has ranges values. So certain range from the minimum value and the maximum value. So we assign that these kind of ranges to the model, then perform the uncertainty analysis. So these are actually result of the uncertainty of the model. So great lines, that is actually concentration change ranges, so that under what if scenarios. So then we can provide these ranges, and then that kind of nuclear safety kind of committee will determine whether this is okay or not under the what if scenarios. So our kind of role is providing the uncertainty of the model. Then committee will decide whether this is good or not. It's safe or not. So then yeah, definitely the uncertainty analysis is very important to Larry Vier's question. Hope that this is an answer to your question. And also, if you need that, definitely I can answer to your additional question. And then next question is Hyoun. She's interested in backward model approach, and she asked if it is possible to evaluate the backward transport, the source tracking of the contaminants entering the stream within the watershed model, including processes in unsaturated zone. Yes, this one is this. Yeah, okay, I can look back to the slide. Sorry about that, and go back to slide. The backward probability model. Yeah, that is also a good question. So here we actually focus in this case we actually focus on groundwater. Sorry, I noticed that my screen is not shared.
Oh yeah.
Sorry about that.
Just all good.
Yeah. So now I show my screen.
Yep.
And
Perfect.
yes, this case we focus on groundwater system and also expand to the variable saturated zone. So yeah, definitely we can identify source of contamination in a variably saturated zone. And this one is only focusing on a groundwater system, a subsurface system, including the variable saturated zone and saturated zone as well. And but not linked to the surface water system. Definitely, we are planning to expand this backward probability model to the integrated subsurface model. Yeah, so maybe for kind of simplified model, yeah. So we you can just kind of simplify the model by applying the kind of applying that river stage. No, just no need to run a surface water system. Just yeah, assume the kind of subsurface model only, and then on bottom of the stream line, then you can assign the contamination or something like that, and also you can kind of start that backward probability model from the detection of contamination, the observation location. Then you can simulate this backward probability model. Then you can find the surface area. You can find the zones where the probability of absorption is higher than a certain range. Then you can kind of select the candidate source zones. Then you can start from that. Then you can run the simulation, integrate the subsurface simulation, then run the solute transport. Then you can kind of simulate that, and then you can compare the simulation result with this observation concentration. So then you can kind of expand that to the surface, integrate the surface and subsurface model. Hopefully, yeah, my answer is helpful for your question.
We have just one more question that I can see in the chat as well
Sure.
from Ricardo.
Oh, okay. Yeah, Ricardo was also curious about the example on water management. Yeah. He wants to know if your simulation have shown a significant dynamic exchanges with the reservoir bank storage as water levels rise and drop in the yes, yeah, definitely, yeah, it is a quite significant interaction, strong interactions between surface water and groundwater system, also bank storage. So yeah, definitely it is depending on the conditions. So bank storage is a highly permeable reservoir, permeable. Then yeah, definitely reservoir and interactions between reservoir and bank storage is very strong. If the bank storage is yeah, that the material is highly impermeable, then probably not that a strong interaction. So, but this case, yeah, this case, the numerical dam, we assume there is not no strong interaction between the reservoir and then dam block. Here, so here. For the numerical dam we develop here is just yeah, block the water, so no kind of no no interaction between a dam and the reservoir, so no water leak from dam blocks, but there is a definite discharge point here. Then we can use a boundary condition linking in the reservoir to the downstream location. Thank you.
Perfect. I don't see any other questions in the chat. Oh, I think we might be getting more. Yep, perfect. I think that's it. Yeah, perfect. Thanks, Hyoun-Tae. Yeah, for anyone that's in the webinar, or yeah, everyone that's in the webinar, we're going to be posting the recording very shortly. So keep an eye on our blog as well as our social media, and as well as our newsletter. And you can view the recording of the webinar in just a few days. I think that should be it. Thank you so much, Hyoun-Tae. And thank you all for attending this webinar. We hope you found it very informative, and we hope you enjoyed.